Dear colleagues, I'm glad to present you our speaker Vladimir Dragović. Vladimir will talk about integrable billiards and extremal polynomials. Please.
Thank you very much. Thank you all for coming. I know that it's, as we discussed with Dmitry just now, this is a very busy, there was very busy spring and now very busy summer for all of us. And still meeting friends and colleagues is always a pleasure. So I will try to talk today about something which occupied my attention in the last few years. And in a sense, this is a continuation of a talk I gave maybe in February or something like that at the same seminar. So, and I also want to thank the organizers of this seminar for providing this platform for integrable systems, which I think is very important. Oops, now it. So what I'm going to talk, do you see everything? Is it okay?
Yes, it's perfect.
Do you see this strip? I have one strip here with participants. Do you see this strip as well?
Yes, yes.
I don't know how to move it. Now it's better, huh?
It's okay.
Okay. Okay.
It's a list of papers. Yes.
Yes, but but there was some strip. I see here also strip of participants. But so you don't see this. This is good if you don't see. I would mostly focus on these two papers, which appear decently. And so I'm going to talk about mathematical billiards as a simplified model, where we forget about everything which makes the real billiard game interesting. So we understand that we have a material point, a particle of unit mass, which is moving without friction inside domain and reflecting absolutely elastically on the boundary. So no spins, no friction. This is a completely idealistic situation. Still, from geometric point of view, and not only geometric, I hope to convince you today, is quite interesting. And this is about, of course, something is not working. Okay. I will, this time, I will focus mostly on higher dimensional situations. So the most interesting things will come with dimension 3 and higher. And you can understand that you can easily visualize that you have a billiard boundary consisting of an ellipsoid, let's say. So it's like a surface, two-dimensional surface in three-dimensional space. And maybe on some space station, maybe they play like this. They maybe have some ellipsoidal chambers, and then they enter into that and then play inside. So they're inside ellipsoid, and then they play this billiard game. And then, of course, elementary differential geometry tells you that the reflection is still perfectly well defined. This slide serves to explain this obvious fact. So when we are talking about integrable billiards in higher dimension, that means that we are talking about billiards within quadrics. And I will explain this a little bit more. And then, so we consider billiards within ellipsoids, and I will use D to describe the dimension of ambient space. So if you are in plane, this is D equal 2. If you are in usual space, this is D equal 3, and so on. And then the question, one of the starting question would be, what is the shortest periodic trajectory? In a sense, what would be the periodic trajectory with the smallest period? And now I need to introduce one important notion about essential trajectory. So if you're talking about billiards in D-dimensional space, then we will say that trajectory is essential if it cannot be studied in D-1 dimensional space. So if this trajectory is not completely placed in some space of lower dimension. So then we will say that this is essential trajectory. Why we distinguish essential and non-essential? Because if trajectory is non-essential, that means that somehow it actually lives in space of lower dimension, then we can use technique of this lower dimension space and study them there. So what we're going to show is that, and this is going to be starting point in a sense, we will do much more than that, but we are going to show that the shortest, in a sense, trajectory with the shortest period essential in d-dimensional space has period of d+1. And then, in order to prove this, we will develop some technique. And then this technique will allow us to do much more. And this is the actual goal of this seminar, is to present for you, in a sense, a complete classification of periodic trajectories of any period n within ellipsoid in d-dimensional space for any d. So for n and d, give me n and d, and I can give you full classification of periodic billiard trajectories of period n in d-dimensional space. This is going to be the outcome of our seminar. But as I said, we are going to deal mostly with the spaces of higher dimension, meaning d greater than 2. But let us start with d equal 2. This is still the basic and still interesting case. So we see here, we are talking about planar case, d equal 2. So this is billiards within ellipses. So given an ellipse as a boundary, and we play this mathematical billiard game. And there are two main regimes. This is a red regime, where you see there is this dotted red ellipse, which touches every segment of this red trajectory. And there is a blue regime, where there is this dotted hyperbola, which touches segments of the trajectory. So in red regime, the segments never intersect this segment defined by focal points. In blue regime, they always intersect this segment defined by focal points. Moreover, these important additional objects, this dotted red ellipse or this dotted blue hyperbola, are always confocal with the boundary. They're confocal with the boundary, and they are caustics of the system, in a sense that for every trajectory, there is such a curve which touches every segment of given billiard trajectory, or the line which is the support of this of billiard segment. And the existence of this caustic, this is geometric manifestation of integrability of this problem. So Pons-Leporism says in this particular case that if we have a fixed boundary and fixed caustic, and if one such a trajectory is periodic with a given period, let's say 3 here, then any other trajectory with the same boundary and same caustic would have the same period. This tells us the following, that we should not ask how many periodic trajectories are there, because if there is one, there are immediately infinitely many. This is probably like with this mosque you mentioned, these flies you mentioned there. So if there is one, there are immediately infinitely many.
Absolutely.
But the right question should be, for the given boundary, how many caustics are there which generate periodic trajectories with given period? And this is the question we are going to take. And now, talking about this planar case, we can say that we know that there are two periodic trajectories in this case. This is one going along a smaller axis and another going along bigger axis. These are two periodic trajectories of period 2. But these trajectories would be non-essential in the classification I mentioned at the beginning, because both of them, they belong to, in this case, a space of dimension, subspace of dimension 1, to this coordinate axis. So periodic trajectories of period 2 would be examples of non-essential trajectories. So the first potential essential trajectory is going to be 3 periodic for d equal 2, like this. And we are coming to the first non-trivial result of today, simple but non-trivial, that for a given for a given boundary ellipse, such a caustic is unique. So there is only, and it is always an ellipse. So why is this always an ellipse? Because if it would be hyperbola, then this segment, every segment crosses x-axis. So in order to be periodic, you need to come back to initial point. That means that you need to cross x-axis even number of times. This simple observation is going to be very important for us. So if you have hyperbola, I'm reformulating what I just concluded. If we have hyperbola as a caustic of a periodic trajectory, then this periodic trajectory is necessarily of even period. That means, coming back here, that 3 in particular cannot be period for a periodic trajectory which has hyperbola as a caustic. And it can be shown that, of course, among ellipses, it can be only 1. You can do it naively because here we see 1, and then if you make ellipse a little bit bigger, then you will see that it will not go into close in three steps. If you make it a little bit smaller, you see that it will go around more. Of course, this can be formalized, and this can be proven exactly in several different ways. But now we are going to d-dimensional space. In d-dimensional space, we define, as usual, in this analytic form, a family of confocal quadrics. So this is depending on a real parameter lambda. So we assume that A1 to AD are distinct real positive parameters. We fix them. And these parameters A1 to AD, they define one confocal family of quadrics. Each quadric is parameterized with a parameter lambda. So you fix lambda and you're getting one quadric. You change lambdas, you're going through quadrics of a given confocal family. Now, from the point of view, and points have Cartesian coordinates x1 to xd. So for a given point with coordinates x1 to xd, there are several quadrics which pass through that point. So here we see in d equal 3 through this point here. I'm showing it. I hope you see my cursor. So through this point, we see there are 3 quadrics from confocal family which pass through. So there is one ellipsoid, one sheeted hyperboloid, and one 2-sheeted hyperboloid.
Vladimir, I'm sorry. You say that it's a confocal family in some higher sense.
What?
What does it mean that they are confocal?
Yes. So if we are in the plane, okay, but in a but I got your question. Let me answer. So if we are in the plane, we have x1 squared plus x1 squared divided by a1 minus lambda plus x2 squared divided by a2 minus lambda equal 1. This is what gives us usual confocal conics in the plane. And we have this analytic representation, and we have this nice geometric representation in the plane that there are focal points, and then indeed these are confocal in that usual geometric sense. When we go to higher dimension, this nice analogy, this nice geometric background of confocality is a little bit lost. There is this, for example, for d equal 3, I know exact place where there is this description of confocality for d equal 3. This is in this famous book, Hilbert Confosen. There is this Russian edition, Nagliadная geometria, I think is the name in Russian. So there is a paragraph devoted to description of confocality for d equal 3. It is involved. It's much more involved in the plane. And for D higher than 3, I don't know the right source for geometric manifestation of confocality. But we are here following this line of analytic description, and as usual, and so this is a confocal family, and so the point is that if you are in D-dimensional space, that through generic point you will have D quadric from confocal family, which are going to intersect orthogonally at that point. That means that we fix x1 and xd as now parameters, and then we solve for various lambdas this equation, and we get these various lambdas. These lambdas are so-called elliptic or Jacobi coordinates of a point in D-dimensional space. So this is very well-known concept used heavily by I'm not sure that Jacobi was exactly the first one to introduce this concept, but definitely he was the one who used this in heavily and used it to solve then the most important integrable system of that time, to solve the problem of geodesics of ellipsoid. So this is described in detail in his 26th lecture of lectures on dynamics of Jacobi. Introduction of these coordinates and application to the problem of ellipsoids on geodesics on the ellipsoid. Moreover, Jacobi, in the same lecture, he first analyzed the question of not geodesics on ellipsoid, but geodesics in free space, which means straight lines. And he derived these sort of differential equations of straight lines with the property that there is a Charles theorem saying, I don't have this on my slides, but there is a Charles theorem saying, if you have a confocal family of quadrics and a line, then there are D-1 quadrics from this confocal family, which are going to be tangent to that line. We are going to call this D-1 quadrics, let's say caustics of the line. And so suppose we fix these caustics. So we fix these caustics here, I denote them Q alpha 1 to Q alpha D-1. So these are D-1 quadrics from this confocal family. And now we are considering only lines which are tangent to these fixed D-1 quadrics. For lines in this set, there is a Jacobi derived the system of differential equations, which are, as you can see, written in terms of holomorphic differentials on hyperelliptic curve. And this hyperelliptic curve is of the form y square equal p of lambda, a1 minus lambda, ad minus lambda, alpha 1 minus lambda, alpha d minus 1 minus lambda. What is the point is that the points which describe these parameters, which describe this hyperelliptic curve, fall in two categories. D of them, A1 to AD, these are exactly parameters of confocal family. So confocal family gives you this A1 to AD, and then alpha 1 to alpha D minus 1, these are these selected D minus 1 quadrics from confocal family, which are the caustics of lines which we are studying now. So let me just tell this once again in a little bit different terms. Suppose that now we are talking about billiard within ellipsoid. So billiard within two-dimensional ellipsoid in three-dimensional space. The point is that then this system will have not one caustic as it was in the plane, but it will have two caustics. There will be two quadrics confocal with the boundary ellipsoid, with the property that each segment or its continuation touches both of these two fixed quadrics which are caustics. And now the existence of these two caustics is now a geometric manifestation of the existence of two additional first integrals, because now the degree of freedom of this system goes up. So with as we increase the dimension, the configuration spacing, dimension of configuration space increases, and the number of first integrals also increases. And in general, in d-dimensional space, if you have ellipsoid in d-dimensional space, then this billiard motion will have d-1 quadrics, which are going to be caustics. They represent d-1 first integrals of that system.
Vladimir, I'm sorry, I'm a little bit, I missed something. Could you repeat the definition of these caustics, which are integrals, which are called?
Yes. So let's go back here.
Vladimir,
let's go back here.
I'm not sure that all the auditory is familiar with the dual quadric. Is it necessary here to say some words about the dual linear family, the dual to the confocal family? Yeah.
No, I don't think it's necessary. I don't think it's necessary. So let's look at this picture once again. So here what we have, this is d equal to, we have a boundary ellipsoid, which is ellipse, and we have one caustic. This is this dotted. This is this dotted. In three-dimensional space, we will have two-dimensional ellipsoid as boundary, like this one, like this ellipsoid would be boundary. And then inside, we will have segments inside of billiard trajectory, and each segment or its continuation will touch fixed two quadrics from confocal family.
I understood.
So this can be non-periodic trajectory. This trajectory can have infinitely many segments, but there will be only two fixed quadrics, which are going to touch every segment of this trajectory. And if we increase if we increase the dimension, if the dimension is d, then we will have d-1 quadrics, which are caustics.
Okay. Thank you.
So now we are going to, as learning from Jacobi, now we are going to study this system using more heavily these Jacobi coordinates. So we fix caustics now, q alpha 1 to q alpha d-1. And then we want to see what are these elliptic coordinates. And the elliptic coordinates are going to live, each of them are going to live in their own segment. So they're going to be these segments of positive semi-axis. These are those where this polynomial p of lambda is positive. And then I have here, so these elliptic coordinates are going to change monotonically within their segments, with the extreme points being the segment endpoints. And then these endpoints of the segments can be reflection of the boundary ellipsoid, touching of a caustic, or crossing a coordinate hyperplane. So we have these, and I will, after I explain this once again, I will now then switch to this simulation I showed last time, but I will show it again. So elliptic coordinates in d-dimensional space, there are d coordinates, and each coordinate has its own segment where it operates. So there is one segment for the first Jacobi coordinate, the second segment for the second Jacobi coordinate, and so on. In each, so while we are going around billiard trajectory, each Jacobi coordinate goes along their own segment, up and down, monotonically, not going a little bit, then stop, then go a little bit. No, they go from one endpoint to another endpoint, then backward from that endpoint to this endpoint, and back and forth. And this, now, the important for our story is the nature of these endpoints. These endpoints can be either corresponding to the reflection of the boundary ellipsoid, this is one endpoint like that, touching of a caustic, and there are d-1 such caustics, or crossing a coordinate hyperplane, and this corresponds to this A1, A2 to AD. So crossing coordinate hyperplane corresponds to A1 to AD, touching a caustic corresponds to alpha 1 to alpha d-1, and reflecting of the boundary ellipsoid in our notation corresponds to lambda equals 0. Now I'm going to switch to this movie and to show you how it works in 2 dimensions once again, which in 2 dimensions is going to show you what I was just telling you now for in general. So now I need to do this switch. This is a little bit tricky moment of this, but I hope it will work. So let's try it. So now you're going to see in D equal to what I was telling you about any D. So we have a point going along billiard trajectory, and the caustic is ellipse, boundary is ellipse. When it touches this boundary ellipse, here the first Jacobi coordinates goes to 0. So first Jacobi coordinates lambda 1 goes between 0 and alpha, and the second goes between B and A. And you see they're going somehow, there is some choreography, but they go monotonically between 0 and alpha, between alpha and 0, between B and A, between A and B. So when it comes to, for example, alpha, that means that it touches this ellipse. If it goes to A, that means that it crosses this y-axis. If it comes to B, so first it will now touch here this 0, and now if it comes to B, look here on the right-hand side, touching B means passing through x-axis. That was with ellipses as caustic. But now I want to show you when you have hyperbola as a caustic. So now lambda 1 goes from 0 to B, and B corresponds to coordinate axis before we head from 0 to alpha. Now alpha is here because alpha is hyperbola, and it is now endpoint of the second segment. So now passing through A corresponds passing through y-axis, and here the second, now lambda 1 goes to B, that passes to x-axis, and now alpha on the second goes touching hyperbola. So again, we are now alpha touching hyperbola, and now going So in D-dimensional space, we will have D segments like this. Here D is equal to, we have 2 segments. The first segment will start with 0. Then depending on the nature of this confocal, of these caustics, for example, here it is hyperbola, then that means that this is the first endpoint of the second segment. If it was ellipse, that was the second endpoint of the first segment. So there is some combinatorics in geometry here telling you, depending on the nature of geometric nature of caustics, how this distribution of these endpoints is going to be. Is this clear, or should I show this once again?
Principally, that is clear. Yes, it's okay. Okay,
good. So now I'm then going to try to go back to my presentation, and then so with the most non-trivial moment, we managed to show this animation, and now we are going back. So this is again what I already said, and now we show this in D equal to. So again, endpoints of segments correspond to reflection of the boundary ellipsoid. That was that 0 at the beginning. touching of caustic, that was alpha in our case, which was in first case and second endpoint of the first segment. And in the second case, it was the first endpoint of the second segment. And crossing coordinate hyperplanes, that was A and B in our case. And now, following this Jacobi and Darboux, there is a way that we can write down this periodicity condition. Now we have, in general, we can say that we have these segments between, here is gamma prime S and gamma double prime S. And then we can integrate this, this system of differential equations written by Jacobi along the trajectory and write down the result on the Jacobian of this hyperelliptic curve. And this is what we're going to get. We are getting these parameters here, NS, which are up to the sign, correspond to the number, and S goes from 1 to D. This is the number of times each elliptical coordinate makes this tour along this segment back and forth along one period. So if we have a periodic trajectory, if we go along a period, we're going along a period of this, along the trajectory, while we come back to the initial point. And because of Jacobi's system of equations, this integral is going to be 0. On the other hand, if we integrate, we can integrate going along these segments for each Jacobi coordinate. And since this is periodic, they will come to the initial point. So that means that each Jacobi coordinate will make integer number of times back and forth along their own segment. And this number of times, up to sign, these are these NS's. These are these NS's. What we are going to conclude is, at some point during this talk, is that there is some law between these NS's. They are not completely arbitrary. In a sense, there is some order in this, how these elliptic coordinates go simultaneously along their own segments. They're not independent on each other in some sense. I'm going to explain this later. So these numbers of times each elliptic coordinate passes on its own segment during one period, this is what we're going to call the winding numbers. So these are positive numbers, positive integer numbers. So we will say that M naught is N, this is the period of N periodic trajectory, and then MS is up to a sign, this NS, which is MS is the number of times each elliptic coordinate. So elliptic coordinates M1 to D minus 1 passes along their segments M1 to M D minus 1 times. These are the winding numbers. Now, we are talking now about this D-dimensional space. And as I told you, we have DAs and D minus 1 alphas. DAs describe confocal family of quadrics. D minus 1 alphas, these are our selected caustics. But the question is, we can order A's among themselves. We can order alphas among themselves. But the question is, what is their mutual order between A's and alphas? So in order to study this, we will introduce B's, which are going to be ordered A's and alphas. So we assume that B1 is smaller than B2, smaller than the B2, D minus 1. And we will also need, and I'm sorry for this, this is some unfortunate moment here, that we also need C's, which are reciprocal values of B's. And then there is interesting theorem of Micheloden from 1994, which I will call in this talk Oden alternative, which says that this order between A and alpha is not arbitrary at all. There is very small freedom. So if you have jade caustic, caustics are ordered, and if you pick jade caustic, then it is either 2J minus 1 among B's or 2J among B's. So there is small freedom here, but very small. And this freedom is going to play a role later. So I will refer to this as Oden alternative. And moreover, the last one, the biggest one among B's is always the biggest A. It's never A alpha, it's always A. So from just this small observation, we can formulate very important principles, very important consequences about parity of winding numbers. Once again, let me remind you this argument we use to show that hyperbola cannot be a caustic of a billiard trajectory in plane with period 3. We said each segment crosses x-axis, and if it's periodic, that it needs to come to initial point, so it needs to cross x-axis even number of times. The same here. Any intersection of coordinate hyperplane for periodic trajectory has to appear even number of times. So if your endpoint of a segment for your given Jacobi coordinate represent coordinate passing to coordinate hyperplane, then along one periodic trajectory, one period of trajectory, of going along trajectory, this needs to be touched even number of times. So that means that if the winding number mj is odd, I'm just reformulating what I just said, then both endpoints of that segment have to be caustics, because if both of them have to be among alphas, because if at least one of them is among A's, then this winding number has to be even. Now, from this odd and alternative, we see that we cannot have 4 alphas consecutive because of this condition. That means that we cannot have 2 consecutive segments with both endpoints being alphas, both endpoints being caustics. That means that we cannot have 2 consecutive winding numbers which are going to be odd. And last but not least, from this that the biggest B is always A, that means that that segment always needs to be touched, passed even number of times. We get that M of D minus 1 is always even. So these are important parity, these are parity properties which we are getting from this odd and alternative. And this simple observation that if a trajectory is periodic, then it needs to pass through coordinate hyperplane even number of times. So these are very important parity properties of winding numbers. Once again, 2 winding numbers cannot be consecutive odd. The last one has to be even, and in the background is that if winding number is odd, then both endpoints of the corresponding segment or Jacobi coordinate have to be caustics. This is very important. And then we can show, using this is a sort of Riemann-Roch theorem, that if we have trajectories of period smaller or equal d, then they have to be placed in a space of lower dimension. This is because of, in a Riemann-Roch theorem, you have the dimension of some space of function is computed as with poles with prescribed divisor are computed in terms of degree of this divisor minus genus and let's say +1. So there is a degree of divisor minus genus. So in a sense, in order to have this space of functions rich enough, if degree is not big enough, then genus needs to go down in order to make this d minus g big enough. So this is a background. So we can conclude by using Riemann-Roch theorem that those which have periods smaller or equal d, they have to be non-essential. We can also show that if we have a trajectories of period d plus 1, they necessarily have the integer part of d minus 1 over 2 pairs of the same type of caustics, and one has to be ellipsoid as caustic if d is even. These are some observations, but let's not spend too much time on that. So many years ago, using these ideas of Jacobi and Darboux, we managed to derive this with Milena Radnović, we managed to derive, so it's now 17 years ago, this condition, which would be sort of a generalization of Kelly's condition in plane. Here we are getting some sort of rectangular Henkel matrix. And the condition is that rank is smaller than m minus d plus 1, but these coefficient entries of this Henkel matrix are Taylor coefficients of expansion of this hyperelliptic function. And this condition can be easily rewritten in form of the question of existence of pair of polynomials with degree m and m minus d, which satisfy that sort of Padet type approximation condition. We knew that for a long time, but however, we didn't know what to do with this until recently. But this condition then can be rewritten in the form that this condition is satisfied if and only if there exists a pair of real polynomials, p n hat and q n hat of degrees n and n minus d, which satisfy that sort of polynomial Pell's equation. Polynomial Pell's equation where this coefficient p curl hat is polynomial of degree 2d with zeros equals 0 and the reciprocal values of these. That's why I introduced these c's. So in a sense, this is a Pell's polynomial equation. And as we know, in Pell's polynomial equation, everything is unknown in a sense. Polynomials are unknown, and this coefficient p curl hat is unknown. And this polynomial, this coefficient polynomial comes here from the information we had before. So B's, let me remind you, B's are this A1 to AD and alpha 1 to alpha D minus 1. So here they're coming in reciprocal value, but this is what it is. So parameters of the confocal family plus parameters of the caustics and 0 determine this p hat. From those who know the theory of Pell's equation know that what we have here actually is, we have here d segments on the real axis, and determined by zeros of this polynomial of degree 2d, 0, and so on. And just let me say that we will have these intervals then C2J minus 1, where these polynomials Q hat have zeros, and let us denote tau J, the number of zeros of this polynomial Q and minus D on each of these intervals. We will call T1 to TD the signature of these polynomials. So what we have here is, we have set of D intervals, D real intervals, C2D, which is 0, then C2D minus 1, which is 1 over, I don't know, B1. This is 1 over BD, sorry, this is 1 over B2D minus 1. This is 1 over B2D minus 2. This is 1 over B2D minus 3, and so on. So these segments, these D segments are determined by A's, A1 to AD, which correspond to parameters of the confocal family, and alpha 1 to alpha D minus 1, which correspond to selected caustics. Now, when does, so what are these, what are the solutions of this Pell's equation? The solutions of this Pell's equation are nothing but so-called Chebyshev polynomials on the system of D intervals. These are extremal polynomials for this system of D intervals. If we have only one interval, then we have a classical Chebyshev polynomial. If we have two intervals, then we are getting generalized Chebyshev polynomials over two intervals, or they're also called Zolotaryov polynomials because they were studied by a student of Chebyshev, Zolotaryov. Then we can have three and so on. What is the point here is, when you start with, let's say, two intervals, when you start with two intervals, you can ask yourself a question: what about the polynomial with minimal uniform norm of degree n, let's say, and harmonic on these two intervals. You get some polynomial. But then what may happen is that maybe this polynomial will still be minimal if you extend a little bit these two intervals. Maybe you still can do something and extend a little bit these two intervals. You get a little bit bigger set, and the obtained polynomial is still minimal for this bigger set. And suppose you do this as much as you can, in order to that you still, this minimal polynomial is still the minimal polynomial for bigger and bigger set. And then the point is that once you reach the maximal set of that with that property, then this set and this polynomial, this set as set of intervals, and this polynomial will satisfy the Pell's equation. So Pell's equation parameterizes not only extremal polynomials, but extremal polynomials and maximal sets at which these polynomials are extremal. So in a sense, everything is tight there. Everything is tight there. When we are talking about classical Chebyshev polynomials on one interval, we don't see this because on one interval, you can use affine transformation and you can take any one interval and you get sort of transformation of Chebyshev polynomial, which is going to be extremal on that one interval. But for two intervals, if you have two intervals, then only a few intervals of only few sets as unions of two intervals are going to be, only special ones are going to be solutions of Pell's equation. So with getting more than one interval, this Pell equation gives non-trivial condition not only on polynomials, but also on this set on which these polynomials are extremal. I hope I managed to explain here something. Any question?
Vladimir, is there some holomorphic interpretation of this property? I suppose that these intervals could be the branch intervals for some Riemann surface. Is it?
Can you say holomorphic?
Holomorphic, yes. Not real, but holomorphic.
So there is I'll explain now. So there is a conformal explanation for that. There is a conformal explanation for that. So we can, and this is the following. So we can consider this set of, let's say, these D intervals, and consider the equilibrium measure of the complement. So the harmonic measure with pole at infinity, and then these ones, which are solutions of Pell equation, are exactly those for which this equilibrium measure of each of these intervals is going to be rational. So this is characterization in terms of harmonic analysis.
Okay.
And then here is this important notion which comes from Chebyshev school. I don't know exactly. Probably it was not written by Chebyshev explicitly anywhere, but I think Borel 1905, and then I think Markov the same year. Definitely there are traces of that. Of the notion of points of alternance for extremal is important structure connected with extremal polynomials. So what are points of alternance? And so for those who had this in school, this is something completely obvious. And for those who didn't have this before, it may be a little bit confusing, but this is as always. So a subset of the, so we consider solutions of P n hat square s equal 1. So these extremal, and I will, let me show you the picture of these extremal polynomials here. So this is one extremal polynomial. This is one extremal polynomial over 3 intervals. So here C6, C5, C4, C3, C2, C1, C2, C1, sorry. So how they are organized? They go from -1 to 1 monotonically, and then from 1 to -1 on this C6, C5. Then between C4 and C5 and C4, they go outside this strip -1, 1. Then between C4 and C3, they go from -1 to 1. then between C3 and C2, this is gap here. This is not our interval. They go above this strip. Then from between C2 and C1, they go from 1 to -1. So our set, these intervals, C6, C5, union C4, C3, union C2, C1, can be also seen as inverse image of the interval -1, 1. So this is exactly points where this polynomial is between -1 and 1. On the gap intervals, this polynomial is either bigger than 1 or smaller than -1. These are these gap intervals. And now, what are the points of alternance? The points of alternance consist of points where this polynomial reaches values either -1 or 1. So here, this point is -1, here is 1, here is -1, here is -1, here is 1, here is 1, here is -1. But we need to select those points. So the maximal set with the property, then it goes alternatively. So from -1 to 1, then from 1 to -1. So for example, here, the set of alternates can consist, let's say, we start from this point, then we include that point, this is -1, 1. Then we can go here, this is -1. But then we need to skip that one because from here and here, it goes from -1 to -1. So we will select this point, this point, this point. We will skip C4, but then we will go to C3, and then we will skip C2, and then we will go to C1. So one set of alternates for this polynomial would be this. This point where it is -1, this point where it is 1, this point where it is -1, then this point C3 where it is 1, and then point C1 where it is -1. I could select some other set. I could say, let's say, this one where it is -1, this one where it is 1. Then I could skip C5, but go to C4 and go here is -1, then go to C3 is 1, then again skip C2 and go to C1. What I want to say is there is some freedom in choice of points of alternance, but this maximal set always has the same number of elements. And this is equal to n+1. And this is equal to n+1. Sorry for this. So once again, points of alternance. This is subset of the solutions of the equation Pn hat square equal 1 with maximal number of elements such that the signs of Pn hat alter on it. And such a set is not uniquely determined. However, the number of its elements is fixed and equal to n+1. This is what I tried to explain on this example. And here we are coming to the first result we got recently with Milena Radnović. This is that there is an important relationship between winding numbers and these signatures, tau j, which is number of zeros of q's on certain intervals introduced recently. So the moral of the story is, apart from these nice formulas, which we got in the first part of the theorem, is that we are getting actually these strict inequalities. So that means that m2d-1 is strictly smaller than md-2, which is strictly smaller than m1, which is strictly smaller than m0. That means that, you remember what are these mj's? Mj's are numbers of time j Jacobi coordinate passes along its segment over one period. That tells you that in a sense, d-1 Jacobi coordinate is the slowest one. Then the next one is quicker than the last one, but slower than others, and so on. So there is a distinct order in velocities, in frequencies, among Jacobi coordinates, and this is very important for us. So we have these parity conditions before we derive, saying that two consecutive m's cannot be odd, and saying that the last one has to be even. And now we also see that they have to be strictly decreasing from m0 to md-1. So the proof of this theorem is based on these basic notions of theory of extremal polynomials, plus one result, which I managed to find only in one place. And this is this Crane-Levin-Nudelman 1990 paper from a book devoted to Kantorovich, They also have some other preprint before that, but this preprint does not contain this. And I also recommend this very nice review of Sodin and Yuditsky from 1992 about these extremal polynomials. I learned a lot from there. However, the result which I need here is not even contained in this Sodin-Yuditsky review. The only place where I found this result is Crane, Levin, Nudelman 1990 paper from a book devoted to combinatorics. And this is the following: that the number of points of alternance of the polynomials Pn on this given segment C to this C2j plus 1 is equal to 1 plus mj, where mj are exactly these coefficients, absolute values of the coefficients in this integral representation, as I told you in our result with Milena from 2004. So what we are getting here is that this mj plus 1 numbers count something. They count something. These are points of alternance. But this 1 plus mj, this counts something on, and these are nested intervals. C2d is fixed, and then C2j plus 1, they're going in order. So we are getting system of nested intervals. And we see that mj plus 1 count something on nested intervals. And since it counts something on nested intervals, it has to satisfy inequalities because you count something on nested intervals. And now small analysis of these points of alternance exactly give you the relation above. And then from this, you have that actually is a strict inequality. So the moral of the story is that amazingly enough, the exact result which we needed here, however vast is the literature about Chebyshev polynomials, extremal polynomials, and so on, I found at only one place, written by three distinguished mathematicians, Crane, Levin, and Nudelman. And actually that was posthumously, I think, that was published after Mark Grigorovich Crane passed away. So now we have all main ingredients. Now we know everything we need to know about our winding numbers. We know the parity conditions, and we now know this monotonicity condition. And then with this, we managed to solve that there were three main, or among main conjectures in the field, and nicely exposed by Ramirez-Ross in 2014. So by this analysis, by these inequalities, we managed to prove all these, all three his conjectures positive. So that is the outcome. So now coming back to our D+1 periodic trajectories. D+1 periodic trajectories. Now we know that these winding numbers need to end with even numbers, so it has to be 2. If the D+1 decides to be started D+1, they need to be strictly decreasing. So there are no much freedom here. It needs to be D+1, D-1, 3, 2. So there is only one set of winding numbers for D+1 periodic trajectories. And their signature has to be, according to our relation, 0, 0, 0, 0, 1. So this is clear. Uniqueness of winding numbers is clear. However, uniqueness of winding numbers is still not giving you uniqueness of set of caustics which generate these winding numbers. For this, we need to do a little bit more. So actually, we claim that not only winding numbers are unique, but caustics which generate such winding numbers are unique. And the proof goes, I'll show you the picture again. So the proof goes from the following. Look, for example, this is in three-dimensional case. This is polynomial which will correspond to D+1 4 periodic trajectories. So this is this extremal polynomial over 1, 2, 3 intervals. So this is D equal 3. We have 3 intervals. This is extremal polynomial of degree 4. It starts with -1, and it has to have the 0, 0, 0, 0, 1 signature. That means that in first this interval, we have this one of these internal extremal points because of this 1, 0, 0, 0, 1. This 1 gives this 1 extremal points. And here, between C4 and C3, there are no internal extremal points because tau was 0 there. And between C2 and C1, there are no additional internal external points. It needs to go from C2 to C1. So what we see here, it goes from -1 to 1 here, then from 1 to -1 here. It has to go like that. Then it needs to come here at -1, then goes to 1, then it needs comes to 1 and goes to -1. The point is that I have here things which are marked as squares. And the point is that these squares correspond to points here. C6, this is 0. C5, this is 1 over A3. Then C4 is 1 over A2. And C1 is 1 over A1. The point is that these C6, C5, C4, and C1, when we do this analysis according to ordinal alternative, these points are exactly reciprocals of A's, not of alphas. And A's, as parameters of confocal family, are given in advance. So for this polynomial, we know it's polynomial of degree 4, and we know its values in 4 nodes, which are given to us. Because this is something which is incorporated here, that we exactly know the values to be -1 in points which are reciprocal to A's, which are given to us. So according to that, we can reconstruct polynomial P4. Once we get polynomial P4, then we solve the equation P4 equal 1. We're getting one solution on this interval, C6, C5, and we are getting 2 solutions on interval C4, C1. These 2 solutions will give us C3 and C2, and these 2 are reciprocal values of alphas. These are reciprocal values of caustics. That means that caustics are uniquely determined. So this is the story. This is how we prove that not only winding numbers are unique, but caustics are unique, which generate trajectories with period D+1. Now, we solve the problem completely for periodic trajectories with period D+1 in D-dimensional space. But now we can use the same strategy to classify all periodic trajectories of period n bigger than D+1 in D-dimensional space. Of course, we will have more freedom there, but we can classify this fully. So, so now I'm going to this n periodic to general situation. We are talking about n periodic trajectories in D-dimensional space, any n bigger than D. So what we say here is, then we can completely describe them. Given an ellipsoid in D-dimensional space and n bigger than D, there is at most one set of caustics, alpha 1 to alpha D-1, of the given types, which generates n periodic trajectories within epsilon, within this ellipsoid having a prescribed signature. So if we fix 2 things, if we fix types of the caustics, and if we fix signature, then and only then, there is a unique trajectory, unique periodic trajectory with given period in D-dimensional space. So fixing type of caustic, that means telling you, is it ellipse or hyperbola, for example, in the plane, or in 3-dimensional space, telling you, is it a 1-sheeted hyperboloid and a 2-sheeted hyperboloid, or 2 1-sheeted hyperboloids, or things like that. And describe signature, I need to give you this sort of 0001 information. Now I'm going to explain this a little bit more. So the proof of the theorem relies on two previous theorems. One is this odd-n alternative, which I already mentioned to you. But when we now trace it exactly in our situation, we see that then it says that if Q alpha and Q beta are caustics of the same type of a given billiard trajectory, then this alpha 1 minus 1, b minus beta minus 1, so reciprocal of alpha and beta, exactly come in this order, C2k plus 1, C2k. So first odd one and then even one. This is something which looks like a detail, but important detail. And the second is important result of Pecher-Stoffer and Schiffermeyer from 1999 about the rigidity of Pell's equation. It roughly says, if you have 2 sets of intervals, 2 sets of D intervals, such that the first, let's say, interval of the first set is the same as first interval of the second set. And then in each of remaining intervals, corresponding endpoint, one corresponding endpoint is the same, then, and in each segment, they have the same number of extremal points, then necessarily the second endpoints of all of these intervals coincide, and these polynomials coincide up to constant. So this is sort of rigidity, which tells you that you have freedom to fix one interval in Pell's equation and one endpoint in each of remaining intervals. Then the second endpoint in all of these d-1 remaining intervals is necessarily determined by the structure of extremal polynomial. So using these two results, we are getting out here. So what does it tell you? What does it tell us? It tells us that we can use these winding numbers for which we have full axiomatization, which uniquely classify periodic trajectories of period n in d-dimensional space. So what is this? So this is a set of these d-winding numbers. The first one is n, this is period. There are no two consecutive odd there. The last one is even, and they're going in decreasing order. This is all. So for each such combinatorial object, there is a unique set of caustics which generate periodic trajectory of period n. Let me show you on a few examples. So for three periodic trajectories in three-dimensional space are placed in coordinate plane, they are non-essential here. For periodic trajectories, they necessarily have this 4, 3, 4, 3, 2. They necessarily have winding numbers 4, 3, 2. So there is only one set of these winding numbers, and there is a unique such set of caustics. It can happen that these two one-sheeted hyperboloids in this case coincide. There are situational parameters, but these two coincide. If they coincide, then we are actually getting something which is completely placed on this. Then segments belong to these rulings of this one-sheeted hyperboloid. And here you see these four periodic trajectories placed on this one-sheeted hyperboloid, which here represents two identified caustics. This is one degenerate case. For 5, if we are talking about 5 periodic trajectories in three-dimensional space, there is only one possibility for winding numbers. There is 5, 4, and 2. 5, 4, and 2, because 5 is odd, that one, the next one has to be even, and the last is even, so it has to be 5. Nevertheless, based on odd and alternative, we have one here branching of situations here. Here, C3 and C4 can be one of them to be reciprocal of A2 and one reciprocal of alpha 2. This choice, is it going to be C3 or C4, reciprocal of A2 or alpha 2, correspond to this choice of type of caustics. So you, depending on this choice, you make this choice of type of caustics here. And the more interesting is, the most interesting among those, of course, are 6 periodic trajectories. Because here, the first time you have several winding numbers, you have several combinatorial options. You can have 4, 6, 2, 4, 5, 6, 5, 4, 6, 5, 2, 6, 3, 2. And so on. Now you can give me any n and any d, and I can give you all corresponding partitions, which each of them, each partition gives exactly unique set of caustics which generate periodic trajectories with given winding numbers. And this is full classification of n-dimensional, full classification of n-periodic trajectories in d-dimensional case. This combinatorics, which arises from this study, actually is quite interesting. And as Israel Moiseiwitz-Gelfand said in 1990, the older I get, the more I believe that at the bottom of most deep mathematical problem, there is a combinatorial problem. I can say that, reaching the seniority of Israel Moiseiwitz, I gradually start to admire this more and more. So together with George Andrews, we managed to study this further, this apparently very interesting combinatorial object. So these are these in integer partitions, where E1 is the smallest part is even, the first axiom, the second, the adjusted parts are never both odd. And then we managed to study this in the usual combinatorial setting, and then it leads to some other also ramifications in theory of partitions, for which George Andrews is the main expert. Okay, I'll stop here. I was a little bit longer than expected. Sorry for this. Thank you very much.
Vladimir, thank you. Are there any questions? Please, it's a good time. Okay, I have a lot of questions. First of all, about the last statement, the combinatorial interpretation of these sets of winding numbers. That does it have an interpretation in representation theory?
This is a good question. So far, I don't know the right answer to that. This is a good question. We are studying now some aspects, but first, not exactly to representation theory, but to some other, but it's not still finalized. So I would not, at this point, I would not say much more. But about representation theory, this is good.
But you see, the nature of my question is geometry. So is this problem of billiards has interpretation in terms of some linear algebra, some geometric object like Grassmannian, like flag varieties, something like this?
It could be.
Okay.
Could be.
Another set of questions.
Yeah, I have some. I can give some interpretation of these winding numbers or generalization of winding numbers in terms of Plucker coordinates in some aspect, but I would need to somehow to derive some story.
Okay. But it exists, so it's something.
I know how to recognize winding numbers and their natural generalization in terms of Plucker coordinates in some sense.
So in some sense, these are the particular values of tau functions of some integrable models. Okay. Another question, another set of questions about.
I think these are good questions. These are good questions, and yeah. Mm-hmm.
About the dynamics. So just the linear dynamics on the line of the billiard, of the trajectory of billiard trajectory. If, for example, we consider this linear dynamics in terms of ellipsoidal coordinates, is it something known, something familiar? Is it some integrable system? So.
But this is I'm not sure that I fully understand. This is an integrable system. Billiards within ellipsoid is an integrable system itself. And it linearizes, as you said, on the Jacobian of this hyperelliptic curve, which is determined with parameters of confocal family and caustics. So
just the linear dynamics along the trajectory of a billiard. It is linear. It
linearizes on the Jacobian of this hyperelliptic curve.
So it's the same as the dynamics over the geodesics on the ellipsoid.
It's similar. It is similar.
It's not the same. It's not the same.
It's not exactly the same. It is similar. Yes.
So it's not a natural question to make just the projection of the trajectory to the surface of the ellipsoid, and to consider, or just to consider the geodesics. So I'm a little bit confused.
So if there is this known construction, if you consider geodesics and then on ellipsoid, and then you squeeze ellipsoid.
Yes.
Then you will get billiard trajectory. In a limit, you will get billiard trajectory on this lower dimensional situation.
But
so if you just a moment. Take two-dimensional ellipsoid in three-dimensional space, and take geodesics there, and then squeeze them appropriately. In the limit, you will get a billiard within ellipse.
Okay, that's it's a very interesting limit procedure. Thank you.
So this is a brother, sister, or cousin of problem of geodesics on ellipsoid, but it's not identical. I mean, it's not that.
Thank you very much. Was very interesting. Other questions? Okay, Vladimir, I'd like to thank you once again, and I hope we continue this discussion.
Sure. Thank you all, and see you around. Thanks a lot.
See you.
I enjoyed being with you.
Bye.
And by the way, did you stop recording?